Everyone to the last and eighth week of the MTV Nuclear Engineering Summer School. I'm proud to introduce today Mr. Colton Graham. He earned his bachelor's from the University of Michigan in nuclear engineering and radiological sciences in 2021. He now is working on his PhD work with Professor Igor Jovanovic, and he focuses on a bit of this for his dissertation work. We'll be talking about time-resolved digital data processing, enhancements in neutron active interrogation. And very much looking forward to your talk today, Colton. Please take it away.
All right, well, thanks for the introduction and good afternoon, everyone. So like Flint said, my name is Colton Graham. I'm a PhD student here at the University of Michigan, and I'm talking about time-resolved digital data processing enhancements in neutron active interrogation. So fast neutron active interrogation is a well-established and powerful technique for concealed contraband detection. The idea essentially is that one uses some source of fast neutrons, often that's a fast neutron generator based on DT neutron or DD neutron fusion, in order to actively interrogate some piece of cargo, either a large cargo container or a smaller luggage sized piece of cargo, within which you suspect there may be some concealed contraband, say explosives or narcotics or special nuclear material. One can then use an array of radiation detectors in order to sense the signatures of that concealed contraband, particularly looking at gamma ray signatures from traditional contraband threats and looking at fast neutrons from induced fission reactions on special nuclear material. Particularly, one can use the energy of those signatures in order to isolate them from background. For explosives and narcotics, those are primarily made up of hydrogen, carbon, nitrogen, and oxygen, HCNO. So one is often looking for gamma rays associated with activation on those elements. The problem is that those elements are hardly specific to contraband, right? There's plenty of benign cargo that's primarily made up of those elements. So in order to distinguish contraband from this benign cargo, one can use the ratio of the intensity of the signatures associated with each of these elements in order to infer some information about the stoichiometry of that contraband, and then use that, of that cargo, and then use that to try to discriminate contraband from benign cargo. For example, a high degree of nitrogen can be indicative of explosives, either just explosive material or a bomb, or a particular ratio of carbon to oxygen can be indicative of narcotics, say cocaine, against other organic cargo that would also contain carbon and oxygen. Now, there's two primary sources of these activation gamma rays. There's thermal neutron associated neutron capture reactions and fast neutron associated inelastic scattering reactions. And when isolating the gamma rays associated with each of these reactions, gamma rays from the other reactions act as a background, right? If you're interested in inelastic scattering gamma rays, thermal capture gamma rays are a major active background. So in order to isolate each of these signatures with an improved signal to background, one can make use of pulsed fast neutron analysis, or PFNA. The idea being to use a pulsed neutron generator in order to create two time regions during the pulse, the prompt time region, and between pulses, the delayed time region, during which fast neutrons and thermal neutrons dominate the neutron flux respectively. So by looking at gamma rays within each of these time regions independently, you can achieve a better signal to background for each of those. But the issue with this is that in order to try to achieve the same total neutron flux as with a comparable continuously operating generator, you have to essentially cram all those fast neutrons into a small time region. So you have during that prompt time region, a relatively intense fast neutron flux, which induces a high degree of pileup in whatever detector you're using to sense that gamma ray, those gamma ray signatures. So that puts a fundamental limit on the detection rate of those detectors, which limits the total fast neutron flux you can use, which limits the sensitivity of your entire system based on the rate of production of those gamma ray signatures, which is based on the rate of the neutron irradiation flux that you use. So in order to increase the sensitivity of your system by using higher fast neutron fluxes, you need to get around this pileup issue. And one potential way to do that is to use organic scintillators. And they're potentially very advantageous for post-fast neutron analysis. They have a very fast response time. We show here measured average waveforms of an EJ309 liquid organic scintillator compared against a few different inorganic scintillators. And the response of these organic scintillators is very fast, faster even than fast inorganic detectors like lanthanum bromide. Additionally, organic scintillators are relatively inexpensive and easy to scale to large volumes. So that means that it's possible to create cost-effective, large, efficient, very sensitive detector systems, which could be deployed at a wide range of ports of entry in order to create a cost-effective and efficient contraband detection system. But there's a problem here, which is that at the relatively low average Z numbers of organic scintillators as compared to, say, inorganic scintillators, the Compton effect really dominates the response of these detectors, right? If you look at the ratio of photoelectric absorption cross-section to Compton scattering cross-section as a function of effective Z numbers for gamma ray energies that are in the range of interest of the gamma ray signatures we care about, which are between, say, 1 and 10 MeV, the photoelectric to Compton ratio for organic scintillators is much lower than inorganics. There's essentially no contribution from photoelectric absorption. So what that means is that there's no photo peaks in the light output spectrum that you measure. So how do you do gamma ray spectroscopy with that? Combine this with the relatively poor energy resolution of organic scintillators when compared against inorganics, and this is challenging. And in order to get around this, you need to use spectral reconstruction techniques. The light output spectrum that you measure from any scintillator is a convolution of a detector response matrix and the true energy spectrum of the incident radiation flux, which is the thing that you're interested in knowing. Now, of course, when you do a measurement, you don't have this continuous convolution. Instead, the light output spectrum that you measure is a discrete histogram of counts, right? So instead, this becomes a matrix equation, where the detector response is defined by the detector response matrix R, and the light output spectrum that you measure you can represent as a vector X, and then you're interested in the true energy spectrum phi. Now, writing that out and looking at the individual components of this, the light output spectrum vector, again, that you measure is just the counts within each bin of the histogrammed light output spectrum. The detector response matrix, you'll note each column of that is essentially just the response of the detector to gamma rays within each energy bin of the true gamma ray energy spectrum that you're interested in. For example, the first column of the detector response matrix is just the spectrum of response to gamma rays with energy within the phi sub naught bin. Similarly, the second column is the next bin, and so on and so forth. So all we need to know is the response of the detector to different gamma ray energies in order to build this detector response matrix. Now, in order to solve for the true gamma ray energy spectrum from the response matrix and the measured light output spectrum, you might think to just directly invert this matrix equation, but this will give you a really poor result, because what you measure is not the true light output spectrum. What you measure is a histogram, which has bins. For each bin is a number of counts, which is selected from a Poisson distribution with a mean, which is the true the true light output spectrum, which is the product of this detector response matrix and the true gamma ray spectrum, right? You're not directly measuring that. So if you do this, noise associated with Poisson counting statistics will be propagated into your solution to this inverse matrix equation, and you'll get a noisy and very poor result. A better idea is to use maximum likelihood expectation maximization, or MLEM. The idea being that one can calculate the probability of getting the light output spectrum that you measure based on the Poisson distribution for each individual bin of your measured light output spectrum, given some true gamma ray spectrum, and then one can then define a log likelihood based on this, and then maximize that log likelihood by iteratively solving for the true gamma ray spectrum, which would most probably give you the light output spectrum that you measure, which when doing so yields this equation for the iterative solution to this MLEM algorithm. So you take, say, in this example here, a measurement with an EJ309 and a cesium-137 gamma ray check source with a measured result shown in red, and then you iteratively reconstruct that true gamma ray spectrum until it converges. Where on the right here is shown the sum square error of that reconstructed spectrum, and you just see the convergence of that as we continue to iterate. Now, the idea to use MLEM and other spectral reconstruction tools to do gamma ray spectroscopy with organic scintillators is not new. This has been discussed a couple times in the literature and in conference literature. We just want to take this existing suite of techniques, adapt them to the particular problem of fast neutron active interrogation, and then show that we can apply these. Now, like I mentioned, this doing this is based on the known detector response matrix, right? But that's relatively difficult to measure with an organic scintillator, as it's difficult to produce gamma rays at each of the individual energies that you need to know the response for. A better idea is instead to use simulation to obtain the response of the detector, which for this work, we use the GEONT4 simulation framework. But that only gets you so far, right? That only gets you the energy deposition simulation. But that's not what you measure. What you measure is a light output spectrum, which is this energy deposition convolved, one, with the calibration of the detector, and two, which is based on a two-parameter linear calibration, and then energy resolution of the detector, which is typically parameterized with this parameter equation here. So you have in total 5 unknown parameters that you need to obtain in order to translate the simulated energy deposition into measured light output. And measuring energy resolution with organic scintillators is non-trivial because, again, you don't have photo peaks. And there's a number of particular measurement techniques which have developed, say backscatter measurements and such. The problem with these is that this adds an additional measurement overhead on a field application, where, say, you want to be able to very quickly obtain updated energy resolutions before each measurement in the field, and you don't want to have individual measurements for this. So instead, what we wanted to do is develop a technique in order to obtain the energy resolution just from, say, standard energy calibration measurements. So in order to do this, we developed genetic algorithm-based spectral fitting, where spectral fitting is not new, but the innovation here is the use of the genetic algorithm. And real briefly, if you haven't used them before, genetic algorithms are just a technique for parameter optimization, essentially in which you allow natural selection to optimize a parameter problem, right? You generate some initial population from the parameter space using Monte Carlo sampling, you test that, you sort it based on its performance, in this case, the chi-square test of how accurate the fit is to the measured data. You select the best performing measures and create a new population by cross-populating genes, parameters, from those best performing members. And then typically you introduce some mutation into those new genes in order to keep the gene pool fresh and to prevent convergence to local minima. And you just iterate this until you have the best performing set of parameters in order to fit your simulated data to measured data. Where the genetic algorithm is particularly advantageous here as it's robust, computationally efficient, and fairly accurate, more so than using, say, brute force fitting or gradient descent, which are more commonly used here. As an example of that, we show here a fitting to measured data from EJ309 with the cesium-137 source, in which we fit in the region of the Compton edge here through that 5-parameter space. Where in the inset, we just show the reduced chi-squared of that fitting. Now, we only do fitting at the Compton edge in order to make this as computationally efficient as possible. So we really only know the energy resolution and the calibration directly at the Compton edge. But we can collectively do this for different Compton edges for different gamma ray check sources, say cesium-137, sodium-22, cobalt-60, but those can then be collectively fit both their energy resolution and the energy calibration from each of those in order to obtain the full energy resolution and energy calibration function for a detector, and then apply that to our simulated energy deposition data in order to obtain the full energy, the full response matrix for a detector. Now, before diving into fast neutron active interrogation, we did some initial testing of MLAM-based spectral reconstruction with different gamma ray check sources, just using a small 2-inch by 2-inch cell of EJ309. And we show that result for on the right here, where for each of the gamma ray check sources tested, we show the measured light output spectrum in blue, and then show the reconstructed gamma ray spectrum in red, where the black dashed lines indicate the energies which we anticipate to observe, i.e. there ought to be some peak in the reconstructed spectrum at that energy. And you'll see that for each of the gamma ray check sources which we tested, the MLAM reconstruction algorithm successfully takes the relatively difficult to interpret and apply recoil-based measured light output spectrum and translates that into a much easier to use and analyze reconstructed spectrum, which has clearly identifiable peaks at the anticipated gamma ray energies. The most significant result here is, of course, the europium-152, which successfully takes the very complicated gamma ray spectrum, emission spectrum of europium-152, and successfully extracts out peaks at all the, accidentally zoomed. I don't know how to undo that. There we go. Successfully, takes this difficult gamma ray spectrum and then has peaks at all the anticipated energies with only minor spurious peaks. And this gives us confidence in MLAM's ability to work in a complex gamma ray environment, which fast neutron active interrogation is. But it's not sufficient that we're just able to extract out peaks at the correct energies. Like I said earlier, we want to be able to use the ratio of the intensity of these peaks in order to get some information about the activation target. So in order to test the accuracy of MLAM to do so at a wide dynamic range, we made a measurement in which we jointly measured a relatively weak cesium-137 source and a relatively intense cobalt-60 source. And in the inset there, we show again the measured light output spectrum in blue and the reconstructed spectrum in red. And then we looked at the ratio of the intensity of the reconstructed cesium peak and the 1.3 MeV cobalt peak as a function of the number of iterations which we allowed the MLAM algorithm to undergo. And you can see that as we allow MLAM to converge, it successfully converges to the true value, where the measured value here is shown in blue in the larger figure, and the true ratio of the source activities is shown in red. So we can have some confidence in MLAM's ability to successfully reconstruct the true ratio of gamma ray signatures in a reconstructed spectrum. Now I'll make a brief note here that we estimated the uncertainty in the source strength ratio by taking our full measurement and partitioning it into individual smaller data sets, and then for each of those small data sets doing the spectral reconstruction individually and measuring the source strength ratio individually, and then estimating their uncertainty in the mean based on the spread and results we get from doing this. Where in B on the figure on the right here, we show that estimated uncertainty is relatively constant with the number of data partitions, which gives us some confidence in this method for error estimation. And this is the same technique that we're going to use for the rest of this talk. Now, for all the gamma ray check source results I've shown so far, these are relatively easy problems because you could sit down and measure with a gamma ray check source for a long time and get really high counting statistics measurements in order to have a good light output spectrum. But that's not the case for neutron active interrogation, right? When we do this, we're always going to be fighting with poor measurement statistics because we want to bring down measurement times, bring down neutron fluxes, and do this with the lowest possible statistics in order to get the best sensitivity and the highest quality detection system. But this is a problem because when you have noise in the light output spectrum, that propagates to noise in the reconstructed spectrum, right? Poor counting statistics will give you a relatively poor result of your reconstructed spectrum, right? And there's a couple of ways to deal with this using, say, under convergence, using convergence criteria. But like we just showed, we need lots of convergence in order to get accurate spectral ratios. So instead, we elected to deal with this issue in the context of the fast neutron active interrogation measurements by using a Gaussian Gaussian kernel smoothing algorithm. Essentially, between each iteration of MLEM, we apply Gaussian smoothing to that using a variable standard deviation of that Gaussian kernel. And this effectively suppresses noise in the reconstructed spectrum while still allowing for relatively intense true gamma ray peaks to come through in the reconstructed spectrum. And based on toying around with this and testing, we use a standard deviation of this Gaussian kernel between 0.015 and 0.02 MeV. Where on the left here, we show an example of a measurement from our neutron active interrogation using different standard deviations. And you can see that for relatively low standard deviations, we get this very noisy result that doesn't align with our expectations. While if we use greater degrees of Gaussian smoothing, we get something that better aligns with what we would expect from the true gamma ray spectrum. Okay, so now that we have a good grasp on the MLEM reconstruction algorithm, we can do some activation measurements. So for this work, we used a Thermo Fisher Scientific P211 DT neutron generator, which you can see a picture of in the upper right here. This has a nominal neutron output of 10 to the 8 neutrons per second, and this is a pulsed 14.1 MeV neutron generator, which we operate at 100 hertz, and has a pulse width of approximately 15 microseconds. And I'll talk in a little bit about what that pulse width and structure looks like. But for these active interrogation measurements, we designed and built a 1.8 ton water-based collimator, which you can see in the picture in the left here. It's plastic bricks filled with water, which we've arranged into this sort of castle around our DT neutron generator, which there's a port in front of, and which we place activation targets in front of that to allow the 14.1 MeV neutrons from the generator to be incident on that target. And then we place our detectors off to the side here in order to be out of the way of the fast neutron flux from the generator, and then use a combination of lead and iron shielding in order to really reduce gamma ray activation backgrounds on that detector. And using a really large collimator like this is advantageous, as it's both effective at reducing the fast neutron background at the spot of our detector, but is also essentially contains the fast neutron flux, which is emitted in all directions from the generator. And in doing so, basically causes all the activation gamma rays to produce locally within the collimator, which creates a smaller solid angle area from the detector's perspective, which we need, really high quality lead shielding to reduce the active background from. Now, we did a small measurement in which we placed an array of smaller EJ309 detectors at different distances relative to the center of the collimator port, and then using PSD and a light output threshold, looked at the fast neutron flux at each detector, and observed that by being roughly half a meter from the center of the collimator, which is where the detectors were placed for the fast neutron active interrogation measurements, you can get somewhere between an 80 to 90% reduction in the fast neutron flux. Now, for the active interrogation measurements, we used a couple of different liquid organic scintillators, mostly a 4-inch by 6-inch EJ315 volume, but I'll also share some results later with a 5-inch by 5-inch EJ309 volume. And we use relatively large detectors, not just for their efficiency, but more importantly, for the shape of the detector response in this context. Essentially, the continuous slowing down range of a, say, 5 MeV electron in liquid organic scintillator is on the order of several centimeters. So what that means is that in a smaller, more standard sized liquid organic scintillator, say a 2-inch by 2-inch cell, there's a pretty good chance of an electron at the Compton edge of many of the signatures that you're interested in essentially escaping the detector without depositing all of its energy. So what that does is that takes the relatively sharp Compton edge of full energy deposition in a larger detector and translates that into a basically sloped response, which you can see in the simulated energy deposition profiles comparing a large to small volume of EJ309 or EJ315 in the figure in the bottom right here. And combining that with imperfect counting statistics essentially results in a response that's much more difficult for MLEM to pick up on, right? Different gamma ray energies look less distinct the less peaked the Compton edge is. So the spectral reconstruction at these higher energies for smaller detectors gives you a very poor performance, and it's very difficult to isolate high energy signatures that you're interested in. Now, I mentioned that we looked at the time profile of the 14.1 MeV neutrons coming out of the generator. In order to do that, we removed our collimator in order to minimize scattering of neutrons, minimize room return from the DT generator, and then used an array of different fast neutron recoil-based detectors and looked at using PSD and a really high light output threshold to isolate fast neutrons, and then looked at the time profile of those fast neutrons relative to a digitized signal from the pulse-forming network of the DT generator. And those results for each of the different detectors, still being organic glass, EJ309, and the Arctis manufactured helium-4 recoil detector, and each of those results of the time profile of those fast neutrons is shown on the right here. And you'll see we get pretty good agreement between each of those, which gives us some confidence in the results here. But most interesting about this fast neutron time profile is this initial spike in the fast neutron flux, which you can see at the beginning of the pulse here. And it has a width of approximately 1 microsecond, which is short on the time scale of fast neutron, of specifically 14.1 MeV fast neutron thermalization in this environment. So what that means is that you can theoretically get a really high signal to background for the fast neutron inelastic scattering associated gamma rays by isolating on the time region of this initial spike in the fast neutron flux. So like I mentioned, we used pulse shape discrimination with the organic scintillators in this work. And we just used the traditional charge comparison method of PSD. And we used that in order to isolate gamma rays from fast neutron events and from pileup events, just using a fiducial cut on the gamma ray region, where you can see an example of that on the left here. And you'll note that in the context of this measurement environment, despite the fast response of these detectors, there's still a high degree of pileup. Now, we were able to really reduce the pileup in this context by shortening digital record lengths. And I should say that for all this work, we used Kane digitizers and digital waveform analysis for our spectroscopy and our pulse shape discrimination. But essentially, in an organic scintillator, the main issue with pileup is that a second event appears within the tail region of integration for charge comparison PSD, which changes the pulse shape perimeter of that event, kicks it out of your gamma ray fiducial cut, and now that event is essentially lost. So in order to reduce the probability of that happening, you can shorten record lengths, allowing each of those individual events to be triggered on individually, and then you can analyze each of those separately. In order to estimate the impact of pileup based on record length, we did some Monte Carlo simulations in which we essentially generated event trains by sampling from the number of events per DT pulse, which we measured, and then for each of those events, sampling from the time profile of all events, and then generating sampled event chains doing that. And I'll note that this analysis is particle type agnostic and energy agnostic, and uses a non-parallelizable model of detector response. So it's a little simplified, but still it's as a first order estimate of the impact of pileup here. So we sample this, and then we say if there's a second event within the record length, which is opened after each event, then we say that the pulse shape parameter of both events is going to be outside of the gamma ray region, and that event is going to be lost. So if we look then at the percent of total data, which is rejected as a function of record length, we see that for the common record length that are used for organic scintillators, say half a microsecond or a full microsecond, you get upwards of half of your data, which is lost as pileup, which is obviously quite poor. Now, typically you use those longer record lengths in order to get really high quality PSD. But because we're mostly interested in high energy gamma rays, bad PSD is not a killer here. So for these measurements, we use record lengths on the scale of 1 to 200 nanoseconds, which reduces the rate of event rejection with pileup down to below 10 to 20%. Now, showing some examples of fast neutron active interrogation measurements, we show here a measurement with a graphite target, pure carbon. Well, the major signature that we anticipate is the 4.4 MeV gamma ray from fast neutron inelastic scattering on carbon-12. On the left here, we show in the A subfigure the measured light output spectrum normalized to the number of DT generator triggers in order to try to normalize these light output spectra to the actual neutron flux. And then in the bottom here, we show the reconstructed spectra from each of those. And you'll note that after doing the active background subtraction, shown in green, and then reconstructing it, we successfully have only a single peak, which is at the energy that we anticipate. Now on the right here, we show the non-active background subtracted results looking at different time regions. Right, in the inset, we show the time profile of gamma ray events, and then identify different time gates, a prompt time gate during the pulse, a peak time gate during that initial spike in neutron flux, a delayed time gate between pulses, and then all events shown in blue. And then in the larger figure, we show the reconstructed gamma ray spectrum from each of those different time regions. And what you'll note is that we get different signal to background for different signatures using different time regions. For example, during the prompt and peak times in green and purple, we see an enhanced signal to background for that 4.4 MeV gamma ray from the carbon-12 inelastic scattering, as compared against just looking at all events regardless of timing. Conversely, if we look at delayed times, we see an enhanced signal to background for the 2.2 MeV gamma ray associated with thermal neutron capture on hydrogen. So this confirms the advantage of using a pulsed generator in this context by giving you improved signal to background for different events based on their timing, despite the associated challenge, of additional pileup due to the use of the pulse generator for this. Now, looking here, we did measurements with a couple different activation targets in order to span the range of those HCNO constituents of explosives and narcotics contraband. On the top left, we show the prompt measurement with graphite, pure carbon. In the top right, we show the measurement with sugar, which is carbon, hydrogen, and oxygen. In the bottom left, we show the measurement with melamine, carbon, hydrogen, and nitrogen. And then in the bottom right, we show the delayed measurement with sugar in order to look at the hydrogen. And you'll see that we can, from these reconstructed spectra, successfully isolate many of the most important of these HCNO signatures, including, again, the 4.4 MeV gamma ray from carbon, the 5.1 MeV inelastic scattering gamma ray from nitrogen, the 6.1 and 7.1 MeV NP gamma rays from oxygen, and that 2.2 MeV gamma ray from hydrogen. So under these measurement conditions, we can successfully isolate in the reconstructed spectra the most important and the gamma ray signatures that we most anticipate to be able to see. Now you'll note that there's, for a number of these, a little bit of offset between the true gamma ray energy that we anticipate, which is shown as the red dashed line, and the peak of the Gaussian in the reconstructed spectra. And that's essentially due to incomplete measurement statistics, right? We have incomplete counting statistics for each of these. And I should say that each of these irradiations were done for half an hour using, say, somewhere between 3 and 5 kilogram large target. But each of these was only with a single detector. So by using an array of detectors, which is possible to do in a cost-efficient way with organic scintillators, you can achieve high-quality counting statistics and improve some of these errors in the exact energy that you're seeing in the reconstructed spectra. Now, like I mentioned, we want to be able to use the ratio intensity of the signatures in order to isolate contraband from benign targets. So to test our ability to do this, we prepared a set of activation targets, which were sugar, which has a carbon to oxygen ratio of roughly 1, and then we added various amounts of graphite powder to that in order to produce targets with a carbon to oxygen ratio up to 4, which is approximately the ratio for cocaine. We then, again, using a 5-inch by 5-inch EJ309 detector, doing half an hour irradiations for each of these, looked at the non-active background subtracted reconstructed spectra for each of these, and then used Gaussian fitting with a linear underlying distribution in order to isolate the intensity of signatures of the 4.4 MeV carbon signature and the 6.1 MeV oxygen signature, and then look at the ratio of the intensity of these signatures versus the ratio of carbon to oxygen in the target, also including the active background, which has essentially a carbon to oxygen ratio of 0 due to the high degree of oxygen in the environment of our measurements here, as well as comparing that against graphite, which is shown on the right here in green, as compared against the other results in blue here. And what you'll note is that as we have an increased true carbon to oxygen ratio, either of our activation target or of the background, as we have a true increase in the carbon oxygen ratio, we see an increase in the intensity, an increase in the ratio of the intensity of the carbon signature to the oxygen signature. And this allows us to define a calibration fitting from which the measured carbon to oxygen ratio of some unknown activation target could be used to infer the carbon to oxygen ratio of that target, allowing you to, say, discriminate cocaine from sugar. And again, there's relatively large error bars on these, but that's because we're using a single detector, and that could be resolved in a field environment in which you use a large array of organic scintillators. So just to bring everything together here, photopeaks are not a necessity to do sufficiently good gamma ray spectroscopy in the context of fast neutron active interrogation. Instead, using spectral reconstruction, recoil-based detectors like organic scintillators can be used to detect and discriminate many of the most important explosives and narcotics contraband gamma ray signatures. And you can use the ratio of the intensity of these signatures in order to distinguish that contraband from benign cargo. And this opens up a lot of potentially very exciting possibilities. For example, plastic scintillators are very easy to work with and very easy to easily fabricate through 3D printing and develop unique geometries to take advantage of the directionality of the gamma ray signatures. For example, to generate, say, a thin rod detector, which makes use of electron escape to really enhance signal, which comes from a specific position within the cargo, to background, which is produced in 4 pi around the detector. Alternatively, Cherenkov detectors, which due to their fast neutron intrinsic insensitivity and their extremely fast response time, faster even than organic scintillators, could be potentially very advantageous in this context. Additionally, Cherenkov detectors have a lot of applications to imaging, which is useful for isolating the position of contraband within cargo. And they're also just very cost efficient for use in wide scale use as a tool for contraband detection. So with all that, I'd just like to take a moment to thank our sponsors at the Department of Homeland Security and the DOE and NSA for funding this research work, as well as thank you all for your time, and I am happy to take any questions. Thank you.
Thank you, Colton, for your great presentation. I enjoyed it quite a bit, and it looks like there were some relevant questions along the way. Didn't have to filter anything, so thank you, audience. Caleb has two questions which are related, and they go back towards the start of your lecture. So if you could go more towards describing the interaction mechanisms and your setup. What Caleb is asking is how do you detect the slow neutrons, right? The thermal neutrons in your scenario. And then what's the difference between rapid, which I assume he means fast, and slow neutron capture?
So essentially, the difference between the rapid and slow neutron reaction is just the reaction pathway. For slow neutrons, right, it's capture on the nucleus, and then that emits a gamma ray. For fast neutrons, it's inelastic scattering, and the neutron scatters off the nucleus, and that produces a gamma ray. From the perspective of gamma ray detection, they're just gamma rays, but you know what reaction mechanism produces the individual gamma rays that you're interested in, right? You know that the gamma rays, the major signature you can see from, say, hydrogen is based on thermal neutron capture, while the major signature you can see from carbon is based on that inelastic scattering. So you can, if you know that's what you're looking for, and you know that's what the reaction is based on, you can use the timing of the fast neutron in order to better isolate each of those gamma rays independent from each other, right? You can use that to obtain a better signal in the background and look at those individually without having mechanical effect. And those are the things that you're interested in.
Thank you, Colton. Just so you know,
There's
I
other
think it
methods
might
for
be the
slow neutron detection. I mean, in this would, oh.
No, that's all right. Colton, the weather is, I think, interfering with your connection. You were kind of breaking up there a little bit on my end. But thank you for your
Sorry.
answer. I think that answered it fully. You're coming through well now, so I'll try and move to the next question. Let's see. Question from Joe here. He asked, towards your MLEM unfolding process, is there anything that restricts your unfolding to scintillators that do not have photo peaks, or could it be used to reduce Compton noise and get better performance with detectors that do have photo peaks?
Oh, absolutely. There's a literature of people using MLEM on sodium iodide and other inorganics with relatively poor energy resolution in order to essentially take your Compton recoil signature and fold that into the photo peak in order to give you better gamma ray spectroscopy. You could absolutely do all this with inorganic scintillators. It's less essential because you have that photo peak there, right? It doesn't make as much of a difference as it does with organic scintillators, but you could absolutely take all of this and apply that, and I think get better gamma ray spectroscopy than what is typically done just looking at photo peaks with inorganic scintillators.
Nice. Yeah, I think that answered that question really well. Follow up to that, I had a related question. So you go to your unfolding algorithm, right? And at one point you show, oh, we can unfold multiple peaks at a time, right? So how flexible is this unfolding algorithm, right? Like, just does it take an arbitrary number of emitters, right? Like how does when you reconstruct the peaks, right? Is there any parameter that you have to feed on the input to say, okay, I'm expecting this many peaks?
No, I mean, it would work just as well with a continuous gamma ray spectrum.
Okay.
All you're getting is just this is the spectrum of gamma rays that would give me the light output. Hopefully that gives you the correct number of peaks that you anticipate. But you and that's what's really nice, and why I was interested in doing this over, say, trying to do neural network based things where you're trying to feed it peak energies and guess and test. This requires no a priori knowledge about what that gamma ray spectrum ought to look like. It's just giving you the spectrum of gamma rays that would give you the best result compared to the light output spectrum, which is really advantageous from a context where you have no a priori knowledge about what's in that cargo container that you're going to go scan.
Cool. Yeah, thank you, Colton. There's a couple more questions, and we have plenty of time here, audience. So please, if you have questions on Colton's work, do add them in the chat. Otherwise, we'll finish early. But another audience member asks, why use a water-based collimator?
Yeah, so obviously there's lots of options to collimate with here, and a lot of people have used lead and iron, as it's actually a really effective 14.1 MeV fast neutron shield. The problem with that is that it's a big pain to work with. This water-based collimator is relatively easy for us to just go pick up bricks and go completely reconfigure this and remove it if we wanted to. If we had a large lead or iron-based collimator, that would be really difficult to move. It's also really expensive and really impractical from, say, a field application perspective if you were to try to do this and go implement it at ports of entry. So it's just more practical to use this water-based collimator, even if from a physics perspective, it might be preferable to use lead or iron-based fast neutron collimation.
Thanks, Colton. Yeah, just to follow up on that, you said it's easier form factor, more practical, cheaper. These collimator, it looks like almost blocks, right? Are you emptying and filling them pretty often, or are you just leaving them filled when you move them around?
Yeah, each of them is like 20 to 30 pounds. So I've just been leaving them filled, and we'll just go move them if I need to reconfigure this. It's pretty feasible to do so. And these are pretty cheap. We bought these from a Doomsday Prepper website. It's meant to hold water in your bunker. But it was only about $1,000 to buy all of these bricks. So
nice.
It was pretty cost efficient to do this. We've just been leaving them filled and mostly just sitting there, just because we haven't had a need to go dump them.
Nice. Yeah. So your lab is ready for doomsday. Good work there. We have another question. Why use a liquid scintillator instead of some sort of solid scintillator?
I definitely think for a field application, a solid scintillator is obviously preferable. And like I said, it'd be very easy to manufacture these. We use liquid organic scintillators because it's just what we had on hand. I definitely would be interested in manufacturing, plastic scintillators or organic glass scintillators that are well suited for this. But for initial testing, we had the liquids on hand. They're easy to use, so we just used them and were able to get these results with them.
Nice, thank you. And then we have one last one. Again, I encourage more questions. I'll maybe try and come up with one more. Aaron asks, what happens if there are multiple compounds in a container that may have different element or isotope ratios?
Right. This is where fast neutron active interrogation gets difficult, right? Is the idea of clutter. That in any situation, you're not only going to have the activation target that you're interested in. You're going to have this big cluttered environment. And I would say that's where imaging comes in. Using an array of detectors, you can look at the reconstructed spectra from different regions, say of a large cargo container, or of even a smaller luggage if you have an array of smaller detectors. And you can use imaging techniques in order to isolate each of those individually. It's definitely not perfect, and I think clutter is not a solved problem for the broader problem of fast neutron active interrogation. But I think that with imaging techniques, it's definitely not impossible, and you can at least get some idea about what the stoichiometry of different objects within the cargo container is.
Thank you, Colton. I think that answers that question quite well. Sort of a follow-up to that from me. You show the cargo scanning scenario right on slide 2. And now you're talking about, okay, we get these signatures, we can focus on different regions with imaging, right? That sounds like you to me that you might start to be strange for statistics, right? So if you were scanning a large container like this and it's going through this portal that you're showing here, how much time, right? Or how efficient does the array, like what's the combination you're looking for to get an effective scan?
Yeah, I mean, I think that in these proof of concept measurements, right, these were 30-minute irradiations, like I said, which I think is really too long for a realistic scenario. Ideally, you want to be able to just move the cargo container pretty smoothly through and be on the time scale of, say, a minute or so. I think that with with lots of organic scintillators, that's not impossible to do, especially using more modern DT generators, right? This was all done with a 1e8 neutron generator, but the more modern, say, Starfire generators are 1 to the 10th neutrons per second, which can really enhance the sensitivity of your detector. So I think that doing that, it's not impossible to bring the time scale of this down to what you would need for a field application. Again, on the order of tens of seconds to a minute. I obviously we have not done any sort of systematic simulation study in order to demonstrate that. This was all just proof of concept work for the MLEM technique for this application. But I think it's not unreasonable to be able to develop this into a field application that meets the needs of a realistic contraband detection scenario.
Yeah, thanks, Colton. That's quite interesting. Makes me think of now you're using neutron sensitive detectors and you've quite increased your neutron background. But yeah, it's future work. Hopefully not during your PhD, hopefully someone else's. But the yeah, so and also I think it's funny there. I'm just gonna ramble a little bit and comment. I see one more question in the chat. Um, Ricardo and I were fortunate to go out to a facility where they did cargo scanning like this, not with a neutron interrogation, but with um, a rototron, so an X-ray interrogator. Um, and this one shows the driver passing through the neutron source, which I don't think would ever get approved.
Yeah.
But the one that we saw, they actually take the cargo containers at a shipping port and put it through a bay, like an unmanned bay that just has the detection array and the source. So yeah, it'd be interesting to see a concept like that with a neutron facility, like you're mentioning.
Yeah, I mean,
Um,
with like a cargo container, right? You could put it on some sort of unmanned thing. And I think that's pretty feasible. Obviously, with a truck, it's a problem because now you're irradiating the driver. I mean, with I think sufficient collimation, right, or say a moving collimator, you could potentially get around this to where the driver is relatively well shielded. And like, I was at Rapiscan's measurements at Lawrence Livermore Lab, where they have a system in which they have a neutron generator and an array of detectors in the back of a truck, and then you would have a driver, drive that in front of, say, a cargo container or a truck, and they have some pretty intense shielding in order to, reduce the gamma ray flux you get on the driver of your company owned truck, right? They have this huge lead shielding in the back of their van in order to reduce the radiation dose given to their driver. So, I mean, I think those are engineering problems that can be fundamentally solved, but it is something you have to think about if you're going to do field applications.
for sure, for sure. And I'm more thinking, like these guys driving these cargo trucks, right? They aren't employees of the facility, right? So
Yeah,
they're probably not going to have their own shielding. But
right.
yeah, no, that's interesting. Okay, we have a couple other questions. This one's very relevant to what we were just talking about. What's the minimum flux, right? You mentioned like the minimum intensity of the source, right? The interrogating source. But what's the minimum flux you think you'd need on your system, or maybe flux per detector, right? Because your system could be very efficient.
Yeah,
What's
it's
a number you might have there?
it's very context specific. Right, it's based a lot on the shielding, how much of that initial signature is going to be scattered or shielded by the cargo container and the cargo. I mean, again, these are 1 to the 8 neutrons for 30 minutes, and that gives us I would say, a decent-ish result, right? A single detector able to detect, a brick or two size of cocaine or an amount of nitrogen corresponding to, a small bomb. So I would say the orders of magnitude of the flux here is is sufficient to be able to reasonably detect, a reasonable sized target. I definitely couldn't comment on what like an actual minimum number is, but something on the order of 10 to the 8 neutron seconds for half an hour radiation is a decent starting point.
Yeah, it's a minimum flux and minimum time, right? So maybe total
Yeah,
statistics on your detector, but
yeah,
yeah, interesting. Last one. I think this should be an easy one. What if there's a human smuggled in the cargo? Would the person
yes,
be at risk? Yeah.
yeah. I mean, they're going to
Yes, they
receive
definitely
radiation
would.
dose, and that's something that other people have commented on for neutron active interrogation broadly. Um, I mean, like a minute irradiation of say 10 to the 8 neutrons per second is not, it is a substantial dose, but it's nothing close to like the annual dose limit for a person, especially if they're in a shielded cargo container. So it is a decent amount of dose, but especially if you're like, if you're not a driver who's going to be passing through this all the time, if you're only receiving that dose once, it is small compared to the NRC set dose limits for a person. So I think that's less of a substantial issue when compared against, say, an operator who's going to be around this all the time and receives a lot more dose.
Yeah, for sure. That makes sense, Colton. But I mean, then when you up to 10 to the 10th, and now they might be going through multiple ports, it might start to be a
Sure.
worry. But
Yeah, it's
um,
definitely not a solved problem for frost neutron active interrogation broadly.
yeah, yeah. Thank you, Colton. I think we can end it early. We only have 4 minutes left, and there's no questions in the chat. But yeah, thank you once again, Colton, for your great talk today. We'll be posting this online shortly once it gets uploaded through the Zoom system. And I'll go ahead and send you a copy too, so you have that on hand. Actually, I see one more person that has their hand raised. We're not going to call on people with the extra time, but I will give you a moment to put a question in the Q&A. We can wait a few minutes for your last question there. And if I don't see it in a couple minutes, we're going to go ahead and close, but feel free to email us. You all should have my email. If you don't have Colton's email, do you have it on your slide deck here, Colton?
I don't think so, but feel free to share it.
Yeah, I'll go ahead and bump the Courtney's email with your email and the recording.
Well, thank you, Flynn, for hosting.
Yeah, of course. Thanks again, Colton, for your talk. And still waiting on that Q&A question. But while we're waiting for that, do some closing comments. Tomorrow, we'll have a lecture on the IAEA, the International Atomic Energy Agency, safeguards and implementation, from Miss Susan Pepper at Brookhaven National Laboratory. She's been in the field for quite a while and has a very good knowledge of the history. And she will be talking very broadly about the International Atomic Energy Agency, the establishment, development, what they're currently up to, what they've been up to. And the IAEA itself, if you're not familiar with it, is the international sort of not quite enforcement agency, but I guess what's the word, surveillance agency for really anything nuclear that goes on around the world. So yeah, it should be quite an interesting talk. Thursday, we'll have a talk from Dr. Alex Kavner, a recent graduate from the University of Michigan here, also with Professor Ivanovic, like Colton. And he'll be talking about much different topic than we've been talking about during the summer school, which is dark matter and neutrino detection. So more of these exotic particle detections, and I think it will be quite interesting. Let's see. All right, it's been a couple minutes. Whoever raised their hand, I did not see your question in the chat, but again, feel free to email us. I'll send a reply to this. And yeah, if you still have a question for Colton or I, we can answer it. Thanks, everybody, and thank you, Colton.